Good morning. So this is our 750 economic growth. And today we are going to look at this computational experiment paper by Kidland and Prescott. And we will have an example of the methodology using a very simple growth model. Okay. So the lecture is based on these two things. You should read the paper if you haven't read it yet. And then there is this very simple growth model that I will use in today's lecture. Okay. So the idea of computational experiment is this. So there are obvious steps. Okay, so this is a stepwise methodology, right? First of all, you need a question. So this could be a particular research question about the issue you are studying, right? And so imagine that this is a paper, right? So you have this research question that you're gonna answer with some computational tools. That's the idea. Now in the second step, you have to decide on the theoretical setup you are using, right? Because here the research question the research question that you're after requires a structural component. Okay, so what you want to do is to choose the test, choose the theory wisely here. And then using that theory, you're going to construct a simple model economy. Okay, and when I say simple, of course, I mean that's a relative term. I mean some models are simpler than the others, some models are more complicated than the others. Here the important thing is that you want to economize, right? So the model should be complicated enough to be interesting and to be relevant for the question you ask, and also it should be simple enough to be useful, right? I mean, it should be, for instance, solvable, or I mean, at least numerically, you could be able to solve this model. In the fourth stage, you want to calibrate the model economy depending on your purposes, right? So the research question you ask and the construction of the model economy directs you in certain regards, and I will show you what calibration is. I will give you an explicit definition, and then show you how to calibrate the parameters of the model. Usually, when I write constructing a model economy, what I mean is parameterizing the utility functions, the production functions, and all of this stuff. And then, of course, the question becomes in the fourth stage, how do we know these parameter values, right? Because if you want to do some computations, we need some parameter value. I mean, we need these parameter values because we want to run the model, right? So we need these parameter values. So this part is the fourth section when we calibrate the model economy. And finally, after knowing the question, knowing the theoretical foundations, having a model economy, and calibrating it, we finally run the experiments, right? So we want to simulate the economy, and we want to see how when I change stuff within the model, this basically is related with my question, okay? When I change some of the stuff in the model and rerun the model, how the results actually change. And those results, of course, the experimental results will give me the answer. Okay, so these are the 5 general steps, and each step is explained. And I will do the same as this is directly from the paper. So the purpose is usually finding a quantitative answer. Okay, so there are different types of questions that you can ask, and there are some of these. I mean, some research questions in economics, of course, requires a computational experiment, and that's exactly these types of questions. So one type of question is the policy evaluation questions, right? So we want to be interested in sometimes you want to be interested in the welfare consequences of certain policies, okay, or the distributive consequences, or the growth consequences, right? So when I change a policy, imagine that there is a government there. The government, um, implements some fiscal policies, and there is the central bank. The central bank follows some um, monetary policies, and then there are other policymakers in the economy in different institutions. They also try to change the courses of action within the economy. So these policies, sometimes we are interested in their effects, right? And observing, of course, these in the real life. That could be one type of question. Also, we could do it ex ante. Before implementing the policy, we can still have a model economy, and we want to see the effects of certain things, right? So we want to see, for instance, the effects of quantitative easing, or we want to see the effects of increasing the marginal income tax, or any other type of tax. Or if you want to look at what's the best use of fiscal resources, the government resources in terms of transfers. You can, let's say, have a couple of different transfers, and you may want to achieve the optimal mixture of transfer spendings. Then you have this model economy, carefully calibrated, of course, for the real economy you have. Then you can evaluate either ex post or ex ante the policies you have. Now, the other type of question is concerning concerned with the testing and the development of the theory, right? Sometimes you have a model. That model could be extended with other stuff, and you may want to see what are the effects if you extend the model in one particular way or in another way. What are the results? What are the certain consequences of some changes in the fundamentals of the model? If you change the utility function, if you change the production function, if you, for instance, compute the instead of the decentralized or competitive equilibrium, sometimes you may want to see the effects of government intervention. Okay, so sometimes you may want to see what would happen in the best possible case when there's no information problem, so the government can intervene in the economy with a social planner's equilibrium. So sometimes you want to see such quantitative implications, and then you use again the computational experiment to answer such questions. And finally, there are other types of questions that cannot be classified into these policy evaluation questions, or the ones that are directly related with testing and the development of the theory. Sometimes you want to be sometimes you are interested in the sensitivity of the results to certain parameters, or you look at the literature, and in the literature there are some types of models that are frequently used, but then you may want to understand what would happen if you make some of the assumptions more realistic, so on and so forth, right? So you may use computational experiment for other types of questions as well, but typically, I mean, this list, these types of questions cover almost all of the stuff that you can do with the computational tools. Now, what are some questions? These are directly from the paper again, and these are actually from real published papers. Okay, so what are the effects of the current U.S. Social Security system on capital formation and intergenerational equity? Right. So this is directly from a paper. What are the potential welfare, wage rate, and terms of trade effects of NAFTA on Canada, Mexico, and United States? And of course, I mean, you can ask this question after NAFTA is actually established, or you may imagine a free trade agreement between Canada, Mexico, and United States, And then you may try to understand the implications of such a free trade agreement between these three countries. So again, it's ex ante or ex post, but here in this question, in this particular example, this is an ex post question that studies the effects of this type of, this is North American Free Trade Agreement. Another example is what are the welfare consequences of the 1986 US tax reform? So obviously there was this tax reform, right? I mean, from this question, only we understand that there was a tax reform in the United States in the year of 1986, and we are interested in the welfare consequences of it. So how does this tax reform affected the welfare consequences? The welfare of the people, of from different income levels, perhaps different types of jobs, different types of ages. Different ages. All of these things could be relevant. Another example, does theory imply J-curve pattern of covariance between terms of trade and the trade balance, right? So you remember that there's this J-curve in the trade literature. So basically, for this question, I believe the authors write a theory, and then they investigate the covariance structure between terms of trade and trade balance. What is the question 5? What is the contribution of public finance shocks to aggregate fluctuations? So that could be also very interesting, right? Because in the economy, we observe some fluctuation in, let's say, output, right? So then we want to understand what is the role of certain types of shocks on this, right? So one types of shocks are real shocks, and other types of shocks are monetary shocks. Some shocks are permanent, right? Some shocks have permanent effects. Some shocks have only temporary effects. So there could be many different types of shocks, and you can actually introduce them. And here in this particular example, the researcher is interested in isolating the contribution of public finance shocks. Okay, so there could be, let's say, 5 shocks in the economy, and one of them is the public finance shocks. So then you want to isolate the effects of public finance shocks from the other 4, right? So then you must have a model where you explicitly define these shocks. You explicitly define production functions, production functions, utility functions, constraints, and decision problems, and then you identify these shocks. Another example, a similar example, would be the contribution of oil shocks to business cycle fluctuations. Okay. Now, the second step. In the second step, you choose your theory. Okay. Now, the important principle here is that the model is not the real world, right? So that's one of the fundamental principles of economic modeling. Okay. So you want to have this model to represent certain features of reality. Okay. But you must always remember that this is not the real world. Okay, so if you follow Lucas, economic theory is defined to be an explicit set of instructions for building a mechanical imitation system to answer a question. So this is important: a mechanical imitation system. Okay, so we want our model, our economic model, to imitate from a totally mechanical point of view, and mechanical in the sense that it will be a stepwise process, right? So there will be production functions, utility functions, and all the decision problems and the constraints. And then there will be certain decisions taken by these individuals, individual consumers, individual firms, the government, the central bank. And then we want the model to replicate some of the things that we see in the real world, right? But it cannot replicate the entire complexity, of course, of the real world. And theory should be chosen very carefully, of course, right? For instance, here the example, Kydland and Prescott give. So the example is about the neoclassical graph theory. So obviously, we know from the RBC literature that some versions of the stochastic, some stochastic versions of the neoclassical growth model is useful. I mean, these versions are useful in understanding aggregate fluctuations. Okay, so if you want to understand the fluctuations in consumption, fluctuations in investment, fluctuations in GDP, you may start with a very simple stochastic neoclassical growth model. You may put technology shocks, you may put labor supply shocks, you may put some preference shocks uh, to the simple, optimal growth model, and then you learn, how to, then you find, of course, a steady state. Then you approximate the model around the steady state using, perturbation methods, or sometimes you can even use projection methods such as value function iteration and other stuff. And then you may study the reasons of the causes of aggregate fluctuations. But then we know we know by heart that neoclassical growth theory is not suitable for development questions, right? So if you want to understand why some countries are richer than others, if you want to understand why some countries, exhibit uh, faster growth rates in the long run than some other countries, then neoclassical growth theory is not very useful, right? We know that the model, uh, the neoclassical growth theory predicts absolute convergence, and even if you extend the model, there is still conditional convergence. So countries in the long run should should all converge to the same or similar growth paths. So in that regard, we know from the very beginning that from the simple theoretical implications of this model, that we know it is not very suitable for studying development questions. Okay, uh, so one particular model that is helpful in a certain research question may not be really helpful for other types of research questions. Okay, so in that sense, there's no unified model that explains. Uh, that is useful for answering every single research question in economics. Okay, there are different models with different types of assumptions, with different structures, and then we use such differences, of course, to understand the real world. So there is no mechanical limitation system that should be used for every single question in economic research. Okay. So what's the message of all this? Well, you should choose your theory very wisely. Okay, you have to sit down with a clear mind and with your pen and paper and your nice coffee, and then you should, after asking the question, you should make some decent effort to choose the theory that is most appropriate for your question. Okay. Now, after choosing the fundamental theoretical system you're going to have, for instance, whether it's the endogenous growth model or whether it is a model with heterogeneous agents, uh, then in the third step, you construct a particular model economy, right? So when I say a particular model economy, what I mean is writing down explicit utility functions, explicit production functions, explicitly defining every single agent in the economy, and so on and so forth. Okay. So when you are constructing a model economy, there are some things that you should be careful of. One thing is that there is usually an optimal choice between detail and feasibility, right? So you want to have a detailed model, obviously, right? Because you may, this of course depends on your research question, but usually the research question is, for this question to be interesting enough, you should add many, many more realistic features into the model. But also, there's a cost to it, right? So if you add too much stuff, too much detail into the model, then the model becomes very complex. It becomes harder to solve, all right? So you must decide on these things, on this detail versus feasibility issue in a careful manner. And usually it's a tough choice. Sometimes you write down a version and then you realize that there is no solution, and then you simplify it. And sometimes you write a version and you realize that that particular version is not really useful in answering your question, because suppose that some mechanisms are shut down because the model is too simple. Okay. Now the important thing is, of course, that the model you're gonna build is gonna depend on your question, as I said before. So it is usually not very illuminating, to criticize a model because it is an abstraction, right? So of course, a model is an abstraction. The important thing is that whether the crucial assumptions are realistic enough, okay? And here we know that those assumptions are not completely, they can, no model can completely imitate reality, right? So any model in that regard is an abstraction, but the important thing is that some assumptions would be entirely auxiliary. So even if you change them, the results do not crucially depend on these assumptions. Some assumptions, on the other hand, are crucial in the sense that when you change them, the entire result disappears. So then, of course, you may want to have a certain degree of realism in your crucial assumptions, right? Because if these assumptions are crucial, then they must be realistic enough, right? And one other principle is that first, you may want to start with something simple, okay? I don't know, sometimes it is easier to work with a Cobb-Douglas production function, for instance, and then you may want to extend this production function into more general and possibly more interesting structures. Usually, it is better if you start with sometimes a linear utility function, right, with risk neutrality, but then you may want to add risk aversion, right? So those types of from simple to more complicated principle is usually very useful in constructing a model economy. At step 4, right now, you have a question, you have a theoretical setup, and you have a particular model economy. Okay, and when I say a particular model economy, once again, what I mean is explicitly written utility functions, explicitly written production functions, explicitly defined decision problems. So all of this is, all of this means a parameterized model. Okay, so you have certain parameters, structural parameters, and certain initial values, of course, because usually these models are dynamical models. So some variables are state variables, and for these state variables, you have the initial values, right? So the question then becomes, how do you know these parameter values? Okay. Now, if you are lucky enough, so if you are lucky enough, you have a very rich data set. Okay, you have a lot of observable variables in the model, and you actually have observations in the real world for these variables, and then you can attempt a fully structural estimation using some likelihood-based methods or some GMM methods. So that could be doable. That is totally feasible as long as you have the data, right? And as long as your model has a numerical solution. I mean, in most models, there is a numerical solution, so it is not a big concern, although computation times differ. I mean, more complex models, of course, require more time and more computing power to be solved. But typically, we can approximate a numerical solution of a model. The problem is the data, all right? Sometimes there are not enough observables, sometimes there are not enough observations. So the sample size is not too large. So econometric estimation of structural parameters may not be feasible, or may not be the ideal strategy. Then what we do is calibration. Okay, so in many papers today, you of course see some parameters to be calibrated and some other parameters of the model to be estimated. So there is a mixed approach as well. But what is calibration? So let's try to understand it. In the very rough sense, this is the process where we assign, through which we assign values to the parameters. Okay. Of course, it is in certain sense similar to econometric practice, right? In the econometric practice, what you do is to look at the data and look at the model and use the data to estimate the model. Okay, and here once again we're going to learn at the end of the process, we learn the parameter values of the model, and those parameter values will be consistent with the data in a certain sense. But the algorithms are mostly quantitative and computational algorithms, not econometric algorithms, and it is a deterministic procedure, not a stochastic procedure. Of course, you can again develop some, you can add some stochastic components into the calibration exercise, but typically we assume that there is this long-run equilibrium, or we assume that there is this particular date. So in the calibration exercises, there's no uncertainty in that traditional sense. Now, in the physical side, let's try to understand what calibration is in physics. Okay. You know the thermometer, right? Celsius thermometer. So of course, it registers 0 degrees when in cold water, water that contains ice, and 100 degrees, right, when in boiling water. Okay, so how can we know that these measurements could be made, right? Well, we know that the mercury element inside the thermometer had this linear expansion path within these degrees, right? So so that's the physical nature of this particular element, mercury. Okay, and we know the expansion of the physical expansion of the element is kind of approximately linear within these degrees, within 0 degree and 100 degree. Okay, so we know that to calibrate those degrees as 0 and 100, right? So if you want to use a different chemical, right, if you want to use a different element, of course you adjust your measures, right? You adjust your measures. So if it is not mercury but silver, I don't know, or sodium, I don't know which one. So it must be liquidified, right? It must be a liquid. So anyhow, I don't know. Or if you are gonna use not water but, for instance, alcohol, right, as the base material that you measure the freezing degree and the boiling degree, right? So then you adjust these things depending on the materials you have. Okay, so the same is true here. Okay, so for instance, in Denver or Mexico, right? So measurements may differ depending on the height and the air pressure. Okay, so in physics, we have such stuff. So there could be many other examples, right? I mean, imagine any tool you have in physical or chemical sciences, for instance, microscopes, telescopes, okay? All of these have certain calibration practices, okay? You know, the distance between two different lenses, for instance, could be important for measuring something, you know, observing something much more clearly, depending on the distance or depending on the lighting, etc., etc. Now, in the economic sciences, we can summarize the calibration algorithm in this way. Eventually, you have a model, right? And model will have parameters, alpha, let's say. So alpha is a vector. And then in the model, there are some exogenous variables, x, and there are some endogenous variables, y, okay? Now, as you see, the solution is writing down endogenous variables as functions of exogenous variables and parameters, right? So this is the model solution. Now, calibration algorithm basically uses the solution of the model, okay? So the algorithm will use the solution and then try to obtain some alphas, okay? Now I have less than a minute, so let me pause here. I'm going to continue exactly where I am right now. Sorry. So it is 9:42. Let's meet at 10 a.m. Okay?
Okay.
Let's meet at 10 a.m. and continue. Bye-bye.